Hello, student friends. Under molecular symmetry and group theory, in today's talk, I'm going to cover the matrix representation of symmetry elements. So let us start with what is matrix. So matrix is simply defined as the alphabets or the numbers are enclosed in a square bracket. So this is one of the example. This matrix having order is 3:3. So 3 rows and 3 columns. So there are various types of matrices. So you might be knowing unit matrix. So in unit matrix, there is 1, 0, 0, 0, 1, 0, 0, 0, 1. Or there is a row matrix. Okay, only there is one row and various columns. So based on that, based on the number of columns, the matrix having order is 1:2, 1:3 like that, or column matrix. So there is simply the one column with many the rows like that. So there are various types of the matrices. So we want to discuss the matrix representation of the various symmetry elements. So first is that matrix representation of the identity symmetry element. So in this, it is also termed as E matrix. So how one can present the matrix for the identity symmetry element. So let us start with x1, y1, z1. These are the Cartesian coordinates for original orientation of polygon. And so x1, y1, z1, these are the Cartesian coordinates before operation. And when you operate E, we are getting the new orientation having Cartesian coordinates as x2, y2, z2. So x1, y1, z1, these are the Cartesian coordinates before operation, and x2, y2, z2, these are the Cartesian coordinates after operation. Then, as we know that when we operate E on any symmetry element, so at the end there is no change in the overall orientation of molecule. So before operation, whatever the orientation is same after the operation. So in another words, one can say that x2 is equal to x1, y2 is equal to y1, and z2 is equal to z1. So here x2 is equal to we know that x2 is equal to x1. So I am writing this x2 in terms of x1, y1, z1 as 1x1 plus 0y1 plus 0z1. Then we know that y2 is equal to y1. I am writing this y2 in terms of x1, y1, z1 as y2 is equal to 0x1 plus 1y1 plus 0z1. Similarly, z2 is equal to z1. So I am writing this z2 in terms of x1, y1, z1 as z2 is equal to 0x1, 0y1, and 1z1. So basically, I am getting these three equations. So these three equations can be written in the form of the matrix as, okay, this is one, x2, y2, z2, this is in one matrix is equal to this 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. So these numbers are included in one matrix into x1, y1, z1. So you might be knowing, this equation can be written in the these types of matrices, or when you simplify these the multiplication of these two matrices, you are getting at the end these three equations. So the equations are written like these matrices. So because of the same, so at the end the matrix E matrix is 1, 0, 0, 0, 1, 0, 0, 0, the 1, and the character of this matrix. Character of this matrix is the 3. Character of matrix means sum of these diagonal numbers. So 1 plus 1 plus 1 is equal to 3. So this is overall E matrix, or character of this E matrix is the 3. So this is one example, E matrix. Then we'll go for the second symmetry element, sigma matrix. Sigma matrix means matrix representation of plane of symmetry. plane of symmetry. Then usually we know that for defining any plane, we need two directions. Either out of three, these are the different combinations: sigma xy, sigma xz, sigma yz. These are the three different types of planes. So either any vertical plane or horizontal plane or diagonal plane having these directions. So let us see sigma xy plane. How one can represent the matrix for sigma xy symmetry, the element. So in this, you know that. Let us see sigma xy. Sigma xy means the plane lie along x and y directions. So in this, you know that. Let us see, x1, y1, z1. These are the Cartesian coordinates before the operation. And when you operate sigma xy on this, we are getting x2, y2, z2. These are the Cartesian coordinates for new orientation. So these are the Cartesian coordinates for original orientation of molecule, and these are the Cartesian coordinates for new orientation of a molecule. Then we know that here the plane lie along x and y reveals that there is no change along x and y direction before operation and after operation. So before operation, after operation, the atoms or groups lie along x, y. These are as it is. There is no change at all. Only change is that along z direction. So because of the same, x2 becomes x2 is equal to x1, y2 is equal to y1, z2 become minus z1. So this is the one only change along z direction. So one can write this x2, y2, z2 in terms of x1, y1, z1. So x2 is equal to 1x1 plus 0y1 plus 0z1. y2 is equal to 0x1 plus 1y1 plus 0z1. z2 is equal to 0x1 plus 0y1 plus in small bracket minus 1 z1. So these three equations can be written in the matrices form as in one matrix x2, y2, z2 is equal to 1, 0, 0, 0, 1, 0, 0, 0 minus 1 into x1, y1, the z1. Therefore, the sigma xy matrix is 1. This is sigma xy matrix. 1, 0, 0, 0, 1, 0, 0, 0, the minus 1. And the character of this matrix is sum of diagonal numbers. 1 plus 1 is 2. 2 minus 1 is 1. So character of this matrix is 1. So this is sigma xy. Similarly, one can solve the sigma xz and sigma yz matrices. So sigma xz matrix is here there is no change along x and z. So here the overall matrix become 1, 0, 0, 0. Here is only change, that is minus 1, 0, 0, 0, 1. So this is sigma xz matrix. Then sigma yz, there is no change along y and z. So here is minus 1, 0, 0, 0, 1, 0, 0, 0, the 1. So in all these sigma matrices, the character of these matrices is equal to plus 1. So this is regarding the sigma, the matrix. And in that there are three subtypes: sigma xy, sigma xz, and sigma yz. Then we will go for I matrix. How one can represent the center of inversion in the matrix form. So like that, let us see x1, y1, z1. These are the Cartesian coordinates before operation. When you operate the I on a molecule, we are getting x2, y2, z2. These are the Cartesian coordinates after operation. Then we know that if you are operating I, the whole molecule is inverted. Means the relation between all these x, y, sorry, x2, y2, z2, and x1, y1, z1 as x2 is equal to minus x1, y2 is equal to minus y1, z2 is equal to minus z1. So these three can be written in the matrix, in the equation form as x2 is equal to minus 1x1 plus 0 y1 plus 0 z1, y2 is equal to 0 x1 plus minus 1 y1 plus 0 z1, z2 is equal to 0 x1 plus 0 y1 plus minus 1 z1. So these three equations can be written in the matrices form as this is one matrix. Then here is minus 1, 0, 0, then 0, minus 1, 0, 0, 0, minus 1, and into x1, y1, z1. So at the end, the I matrix is minus 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1. So because of the same, the character of this matrix is the minus 3. So, okay, in this the talk, I have covered the E matrix, then sigma matrix, and then okay, lastly the I matrix. So, okay, in the next lecture, I am going to cover CN matrix and SN matrix. Thank you.